Hello everyone. I hope you all are doing well. So today we'll be starting with the most difficult and the most important part of calculus, which we call as the integration. Now, integration more or less you have studied an overview in your physics. This is basically the reverse of what we did used to do in differentiation. So in differentiation, we used to generally find out the slope. Now from the slope, we are trying to find out our function. So that is what our integration is basically. So let's look at the subtopics that we would be covering. Again, this chapter has quite a few number of formulas in it. However, this chapter requires a lot of practice because once you have practice of a lot of questions from this chapter, you would be able to solve any type of questions that are asked from this chapter. So again, while I'm teaching the theory as well, I've taken up a lot of practice questions for you for so that we all can solve it together. I would recommend you all to first pause the video, solve the question by yourself, and then look at the solution so that you would know at where are you making mistakes, and if you were able to solve it, then well done, you are getting the good grasp of indefinite integration. So first in this chapter we'll be looking into a brief introduction of indefinite integration. Then we'll be looking at some standard formulae which you will be needed to remember. Of course, those are some standard conversion of any function to its integral. Then we will be looking at two different methods of doing integration. One is the substitution method, then the next is the by parts integration. Then we'll be looking at a few more other classic and trigonometric integrals which have their fixed integration. So you will be asked to remember those as well. So let's start. Again, as I mentioned, what is integration? It is basically the reverse process of differentiation. So in differentiation, let's say if I used to have my function as x square, then after differentiating it used to become 2x, right? Now what will happen is now I'm integrating it. That means I need to get my original function back. So from 2x, I need to take it to x square. So that is what integration is. Now integration is mostly of two types. So let me write it down. So integration is most basically of two types. One is known as the definite integration and the other one is known as the indefinite integration. So what is my indefinite integration? In this lecture, we will be looking mostly in indefinite integration. So indefinite integration means where my limits are not fixed. So first of all, if let's say I was to tell you about the integration of whatever function has been given to me. Let's say this is a function. So what do I mean by the integration of this? So integration means the area that this function is covering with the x-axis. That is known as my integration. So now let's say if I bound this area with some limits. Let's say this is my lower limit a and this is my upper limit b. So I am basically going to integrate this function from a to b. So this would be known as my definite integration. And when the limits are not fixed, that means I'm going to integrate the entire function in its entire domain. That time we call it as the indefinite integration. So in this lecture, we would be mostly focusing on indefinite integration. Then next we have a chapter which is on definite integration as well. And then we have one more chapter related to this only, which is known as the area under the curve. So these two chapters will be mostly looking at the limits which have been bounded. In this chapter, we have no bound of any limits, so we'll be just learning how we can integrate different type of functions. Now, if I was to show you the representation of any integration, of course, you all know this very well. Just a revision for the representation. So this symbol here represents my integration. This is known as the integral symbol. I have an integrand. Integrand is the function which is going to get integrated. Dx is the value which shows the variable which I need to integrate. So let's say if I have a dx here and I have a y variable also inside. So y would be considered as a constant. I will integrate only those functions which are in the x format. And this after integration would give me x square. Of course, for 2x, we know our integration would be x square. And then we would have a constant of integration as well in the addition. Now, why is this constant of integration coming? So whenever we write down the general solution, of any integration, we add this constant of integration. So why is that? Let's say if in my differentiation, let's say my original function was x square plus 1. Let's say this was my y. So what would my dy by dx be? It would be 2x, right? Let's say if my function was x square plus 3, what would my dy by dx be? It would still be 2x, right? What if my function was just x square? My dy by dx would still be 2x. So that is why whenever we are integrating 2x to go back to our function, we do not know whether there was some constant or not, because whatever constant is there, upon differentiating, the constant becomes 0, right? So that is why there is no constant. So whenever we integrate any function, again, when we are doing indefinite integration, now this is applicable only for indefinite integration, where the limits are not mentioned. Had the limits been mentioned, it would have been, let's say, 0 to 2 or whatever. The limits would have been mentioned on the integral symbol. If it is not mentioned, you have to consider it to be indefinite integration. That means I have to add a constant of integration in my final answer as well. Now, as I mentioned, there would be a lot of standard formulae that you would be required to remember. So here are a few. Let's say if I have to integrate just any constant dx, here I have, let's say, 1. So 1 dx, if I integrate it, it would become x plus c. A to the power x, its integration remains same. A to the power x, it would become a to the power x upon log a. Integration of 1 by x, it becomes log x plus c. Now generally this log has the base e, so we can write it down as ln x plus c as well. If I have x to the power n dx, so this can be written as x to the power n plus 1 upon n plus 1. Here we are considering that n is not equal to minus 1, because of course, if my n becomes equal to minus 1, then in my denominator I would have a 0, which is of course not defined and cannot be found out, right? Now about talking about the trigonometric functions, few we all remember how our differentiation used to work for each and every trigonometric function, right? Now the reverse would same be for the integration. So my integration of cos x would become sin x. Integration of sin x would become minus cos x. I hope you all remember if we were finding out, let's say, differentiation. So for my sine, my differentiation used to be cos x. For my cos x, my differentiation used to be minus sin x. So similarly, for integration of sin x, it becomes minus cos x. Sec square x, it becomes tan x. Cos x square x, it becomes minus cot x. Sec x tan x, it becomes sec x. And cosec x cot x, it becomes minus cosec x. So again, just the formulas of differentiation taken in the reverse order. Now, a few more formulas that you need to remember. Let's say if you need to find out the integration of tan x dx. So how are you going to do it? Again, these are certain standard formulas which you need to remember. If you remember it, it would become very easy for you to write it down during your examination. Else, let's say if you do not remember it, still I'll show you the proof. Based on the proof, of course, you can calculate it during the examination as well. So let's say if I have integration of tan x dx. So here we will be using a little bit of method of substitution. So how can I write my tan x? My tan x can be written as sin x upon cos x dx. Now I know that in my denominator I have cos x and in my numerator I have the differentiation of cos x. What used to be my differentiation of cos x? Minus sin x. So what if, let's say, I multiply a minus 1 above and a minus 1 outside as well. So again, constant can be taken outside, inside the integration. It doesn't matter, right? So I would have a cos x left inside. Now what I'll do is I'll assume this cos x to be t. If this cos x is t, that means if I differentiate this, this would become minus sin x dx is equals to dt. So after this, we would have, if I now simply start replacing the values, I would have a dt here and a t below. So now if I integrate this 1 by t dt, what is the integration of this? Ln t plus c. And what was my t that I had assumed? It was ln of cos x. This is my constant of integration. So you can see this is exactly what we've gotten. Now cos x, I can replace it by sec x. I can write my cos x as 1 by sec x. So I would have sec x to the power minus 1. And of course, in logarithm, we can take the power of minus 1 outside the logarithm. So it can be written in that way. So again, all these formulas, you can prove them by yourselves. This was just for you to show you the proof so that if, let's say, during the examination, you forget the value of integration tan x, cot x, sec x, and cosec x, you can simply calculate it by using this type of method. Now again, a few more formulas for inverse trigonometric functions. These are all our inverse trigonometric functions. For sine inverse x, we remember our differentiation used to be 1 upon root under 1 minus x square. So again, the reverse is here. For cos inverse x, you must remember that there should be a minus 1 upon root under 1 minus x square. Now, one thing here is that, let's say if I had integration dx upon root under 1 minus x square. Now I know this integration is simply sine inverse x plus c. Sometimes what I can do is I can also assume this to be minus cos inverse x plus c. And this is equals to sine inverse x plus c. So keep this thing in mind. Basically, sine and cos, since they are co-ratios, so they work in conjunction with each other. So do not mess up the negative sign here and there. So keep this thing in mind. For tan also, tan and cot also, the main variables and the constants are same. The only thing is that in cot you have a minus sign separately, and in tan you have all the positive values. For sec and cosec as well, the same thing. Now again, as I mentioned, it would be same for cot as well as cosec as well. I can write down my integration of dx by 1 plus x square as tan inverse x. I can also write down the same integration as minus of cot inverse x. So keep that thing in mind. Now here are a few properties of indefinite integration that you must know. Let's say if I have integration of first function plus second function, I have two terms here, so I can separate them out as two different integrations. If I have integration of any constant multiplied with a function, the constant can be taken outside the function. If I have integration of f of ax plus b, I can simply take the after the integration, I can multiply 1 by a later on. So basically the integration. So let's say if I differentiate my f of ax plus b, let's say if I try to find out the differentiation of this, what would it become? It would become f dash of ax plus b, and then I would have to apply the chain rule to find out the differentiation of ax plus b. What would it be? Simply a, right? So that is why I have an extra a here, right? So just to counter this a, I have to multiply 1 by a in my integration. So I hope you all have understood this. Let's look at this question again. A very basic question. They've given us that integration of dx by x plus x square is px. Then we need to find out the value of x to the power 6 upon x plus x to the power 7 dx. So what we'll do is, simply if you look at this equation carefully, what you can see is if I take x common in my denominator, I would have x plus x to the power 6, right? Sorry, I would have x into 1 plus x to the power 6. Now in my numerator also I can try to create 1 plus x to the power 6 minus 1, so that I can have 1 by x plus x to the power 7, which I can write down as px, because that has been given to us in the question. So how can I solve this integration? This is my x to the power 6 upon x plus x to the power 7 dx. So what am I saying is that I'm writing this as x to the power 6 plus 1 minus 1 upon, I've taken x common, so this would become 1 plus x to the power 6 dx. Now I can separate out my two terms, so this can be written as 1 plus x to the power 6 upon x times of 1 plus x to the power 6 minus of integration 1 by x times of 1 plus x to the power 6. Now, of course, you must write dx in each and every integration. If there is no such term as dx, of course, you cannot integrate it, right? So let's say if in future also, if I forget writing dx, do not consider it to be wrong. It is just for me to solve the question quicker. So here, 1 plus x to the power 6, 1 plus x to the power 6 gets cancelled out. Integration of 1 by x dx, this becomes simply ln of x minus, now I have 1 upon, now I can simply multiply my x inside this bracket. I would have x plus x to the power 7. Now this integration, they've given us that it is px. Now I'll also add a constant of integration at the end as well. So this is my answer. So this becomes the integration of x to the power 6 upon x plus x to the power 7. So this is my answer. So again, you must try to create patterns so that your integration can be simplified, and then you can find out your integration using the standard formulas or the reverse order of differentiation that you know.